In this video we're going to be looking at how we could go about designing a power supply for, could be an embedded circuit or a portable device, or in this case we're going to be using an example of an automated remote control car. So this was actually one of my project students' problems a few years ago, and they had to come up with a DC power supply to supply all of the various I/O devices that was going to be on this remote control car, and it was going to be powered by a lithium polymer battery which was nominally 7.4 volts. So the problem is, simply stated, that we have an input voltage here, we have a number of output voltages, 3.3, 5 and 2.5, and I want you to design a power supply that is going to be able to supply each of these devices. Now, in order to do that, what I normally like to get students to do is actually to, just as I've done here, but actually in tabular form, tally up the amount of current required for each of the voltage levels. So we've got 5 volt, a 3.3 volt and a 2.5 volt rail, and in total the 5 volt requires 150 plus 150, 300 milliamps. The 3.3 volt requires 300, 400, 450 milliamps, and the 2.5 volt in this case requires 20 milliamps. So start with, tally your current requirements. Right, very important when you're doing this design. Obviously you've chosen the I/Os, you know which voltage levels they're running at, to then work out how much current that you require. And you can find that information from the data sheets of each of the devices. They'll give you a normal operating current or active current. And we're always using the maximum current here. We're not talking about, oh well, I can put our control system to sleep mode which will draw picoamps. Well, that's no interest to us. We need to design for the maximum current. One other thing we need to take into account is, yes, our LiPo battery says 7.4 volts on it. Well, in reality it goes from 5.4 volts up to 8.4 volts when it is fully charged versus when it is discharged. So we actually have a voltage range for our input voltage, which is where things like line regulation becomes very important. So too does load regulation when, for example, we start shutting down some of these devices when the unit's running. So from there I like to do a block diagram. Alright, so we have our voltage supply, or V in, which then comes through some sort of protection circuitry, which we're going to talk about shortly, and then through into the 5 volt regulator and through to the, we'll do them in the same color as they've been done here, 5 volt I/O. Now the choice you have now is that whether or not you decide to then, for example, we could take our 3.3 volt regulator and connect that effectively in parallel. Now if we do that, the advantage is that this regulator doesn't have to supply any current to any of the lower voltage loads. So this guy only has to be designed for, in this case, 300 milliamps or so. The downside is that the voltage drop across our 3.3 volt regulator is going to be much larger. So there's our 3.3 volt I/O. So in this case it would be, in the worst case scenario, 8.4 volts minus 3.3 volts times 450 milliamps will be the power dissipated across this device. What we could do is, in series with the original 5 volt regulator, we could then place our 3.3 volt regulator. Now the volt drop is only 1.7 volts instead of the approximately 5 we had before, and therefore the power dissipated across this device is going to be much lower, and therefore should be more efficient. And so we can do the same thing again down to our 2.5 volt regulator, down to our 2.5 volt IO. And that's typically how I design my power supplies. Doesn't always cascade them in a fashion like this, but normally it's something a way that I go about it. Sometimes in here you might have a switching power supply. Alright, normal reason for doing that is if you have a large difference between V in and V out. Right, that's where they're very, very efficient and can be used. However, they're often quite noisy, and therefore you will normally always have linear voltage regulators in series with it to help filter out that noise. So I'll put a little star here. That's optional if you have a large voltage difference. In our case, the minimum is 5.4 to 5, so we've actually got a very small voltage gap there. So a switching power supply is of no use here. But this is normally the way I go through it. Okay, so starting by tallying current requirements, drawing a block diagram, then I can now fill in the current requirements. So in this case, I need 20 milliamps for the 2.5 volt, 450 milliamps here, and 300 milliamps here. We see that therefore the total current required to be supplied by the 3.3 volt regulator is 470, the sum of both of those, and the total by the 5 volt regulator is the sum of both of those, 770 milliamps. So you can see what I mean, that by cascading it we run into this problem where each regulator above has to carry all the current of the lower regulators. In reality, I normally uprate my design. Alright, so I would say this one for, let's say, 30 milliamps, and therefore I would uprate this one to probably at least 550, and then this regulator probably to 800 or so. In fact, probably a little higher, maybe 900. Okay, so these numbers are with a buffer, right? Just to over design this application rather than undesign it. Design it for the worst case scenario. Okay, worst case design with power supplies. You're not designing it for when it's operating normally, drawing 100 milliamps. You're designing it when everything's on and everything has to be powered up, and that's what you have to design your power supply for. Alright, so that's basically our power supply now. What I want to look at next is what do we need in terms of protection circuitry. Now, it just so happened in this particular example that this IMU here was worth about $2,000 US. Alright, so we very much do not want to blow that up. So we want to make sure that this circuit is as safe as it can be for powering those devices. So the first thing I want to look at is under voltage protection. Now, because this circuit is running on a battery, and because it is actually on a remote control car which could crash into a wall, it is very likely that if the current drawn by the motor exceeds a few amps, then our poor old battery voltage is going to drop away with it. Okay, and that could happen to be much lower than the 5.4 volts, shutting down the entire control system. So what we want to do is ensure that we've always got a little bit of buffer, a little bit of reserve energy there, so that we can keep our voltage high enough even during the time of crashes and stalls, okay, for a brief period of time. What you see here is a very large capacitor, 56,000 microfarads, and it might look something like this. Obviously that's a 470, but something really large like that. So what you have in parallel with the battery and a switch, you have a very large capacitor, and that acts as basically a buffer or a storage tank. Ooh. Buffer, storage tank. Now, a couple of things you need to think about when you design one of these is that a capacitor is like a short circuit when discharged, So we don't want the poor old battery all of a sudden supplying 30 amps to charge up our capacitor, or whatever that value may be. So we place a small series resistor to limit the inrush current. Small because we don't want a large voltage drop across it, we're only trying to limit the inrush current. We also put in a Schottky diode, diode with a low voltage drop, Schottky being around about 0.3 volts. Once again, remember we've only got 5.4 volts coming in, and the worst case scenario, worst case design, therefore to get 5 volts coming out, it only leaves us a 0.1 volt drop across our 5 volt regulator. So 0.7 here would take us much below 5 volts and wouldn't work. That Schottky diode there prevents the capacitor discharging this way, don't want that to happen, and charging the battery up. We only want it to supply current and to maintain the voltage for the remainder of our circuit. So that's under voltage protection. It's not always required, in fact it's very seldom required, but in this particular instance, being battery powered with something that could stall with a motor was actually quite useful. This is a much more common one. Overcurrent protection. Easiest way to do that is a fuse. But rather than use a cartridge fuse, or one that actually has a filament that burns out, what I've decided to use here is a polyfuse. And a polyfuse allows you, a polyfuse automatically resets after the fault is cleared. So it has a very nice feature that it's auto resetting. This one's rated for 2.2 amps, so that's much more than what we need up here. The total current 900 milliamps, but for fault conditions 2.2 amps, it's going to trip pretty quickly there, and I believe that 2.2 value was chosen based on availability. Right, so polyfuse is a nice option because it automatically resets itself. Perfectly fine to use cartridge fuses as well, or any other overcurrent protection, but polyfuses are a cheap and easy solution. And then finally, protection circuitry that I also included in this design was overvoltage protection. And this circuit is what's known as a crowbar. Circuit, and basically how it works is that if the voltage across that Zener diode exceeds the Zener voltage, so in this case 5.6 volts, where we actually want 5 volts coming out, it's going to turn on this SCR, or silicon controlled rectifier, which is going to short out the 5 volt rail down to ground. Shorting it out, it's going to cause a huge amount of current to flow, which is going to pop this fuse up here. Alright, so when the voltage exceeds the Zener voltage, it's going to trigger this SCR, which then shorts out that supply rail, preventing the overvoltage scenario and popping the fuse. These resistor and capacitor here prevent false triggering of our SCR. Right, small time constant, and keeps it held low. So that's one way we can implement overvoltage protection using what's known as a crowbar circuit. So finally, for the specification that we have up here, this was the final design that I came up with the students. Alright, so we have the battery here, 5.4 to 8.4 volts through a switch, through the undervoltage and overcurrent protection, and then through to the 5 volt low dropout regulator with associated decoupling capacitors. Alright, like I showed you in the previous lecture, 10 mic, 100 nanofarad, in this case 6.8 was recommended by the data sheet, then to the overvoltage protection on the output of that. I was only interested in protecting the 5 volt side because that was the only one that had the $2,000 I/O device on it. From there, the 5 volt line connects here through the 3.3 volt regulator, and then from there through to the 2.5 volt regulator. As you'll see, the 5 volt regulator chosen was rated for 1 amp, 0.8 amps for the 3.3 and 0.15 amps for the 2.5. So they were very much overrated, but that's fine. These are the cheapest options that met the specifications of the circuit. Do note there's lots of decoupling around your power supplies, and you want these capacitors to be physically as close as possible to where you actually mount those ICs. Choosing these was basically a job going through element 14, having a look at the data sheets like I showed you in the previous one, output voltage, rated current, dropout voltages, regulation, and so forth, as well as cost, availability, and pricing. And you'll also note down here that I like to have an LED for each power rail. That way if I see 3 LEDs on, I've got all 3 power rails working, so I can quickly eliminate if I'm having problems with the circuit not working. Alright, so to summarize, in terms of power supply design, things I like to do is once you've worked out all your I/O and your voltage rails, tally the amount of current that you're going to require, draw a block diagram of how they're going to be connected together, and fill in those currents so you can work out exactly what each of your power supply voltage regulators are going to require. Remember, you may need a switching regulator if you've got a large difference between V in and V out. Otherwise, you can safely use linear all the way through and still be reasonably efficient. And if you've got a need for protection circuitry, under voltage, you can use a large capacitor. Over current, use a fuse. Polyfuse is quite a nice solution. And over voltage, using this crowbar circuit. And you might like to use this circuit as a reference going forward. Remembering you won't always need necessarily all of those circuit protection features. However, ones to have always is over current. Under voltage, over voltage is up to you on your particular circuit.